Good morning. It's installment 2. This is stratospheric ozone depletion. This lecture really is going to focus on what the benefits of stratospheric ozone are and how it forms. Some of the history. We're going to describe some of the history of the stratospheric ozone depletion and what has led to depletion and the hole in the ozone. And then explain some of the effects of reducing ozone depletion and kind of talk about where we are now with it. And yeah, so we'll launch right into it. So stratospheric ozone is in the stratosphere. It is beneficial. We talked about being in the troposphere, how it is an irritation to lungs and actually like breaks down the protective lining or layer on plants and causes some plant damage. But stratospheric ozone, so not in the troposphere, but in the stratosphere, it accumulates roughly 45 to 60 kilometers above the Earth. And it has the ability to absorb ultraviolet radiation and protect life on Earth. And so we have a spectrum of UV light. We refer to UVA, B, and C. And A is like the least damaging, and then B and then C is the most damaging, and they're really like based on those energies that are in those particular wavelengths of light. And stratospheric ozone filters most of the damaging, like the most damaging stuff is what it really works on. So what's ironic is that that's what produces ozone in the stratosphere as well. So UVC radiation actually breaks the molecular bond holding together diatomic oxygen. So diatomic oxygen, anytime there's like a two diatomic, those diatomic oxygen compounds are really tightly bonded together, and it takes a lot of energy to break them apart. But UVC has the amount of energy that it would need to excite those molecules enough to where they're willing to let go of one another and to be just free oxygen and oxygen. A free oxygen atom produced in this first reaction is going to encounter another diatomic atom somewhere along the way, and it's going to say, hey guys, let's hang out, and it will become a triatomic molecule of oxygen, and that is ozone. Both UVB and UVC radiation can break down the UV3 molecule. So there's just like creation of O3 and then the breakdown of O3 that's just constantly happening. And in equilibrium, there is a layer that is significant enough that it's going to filter out UVB and UVC, a lot of it, to protect us. I mean, that's the benefit of it, is that it protects life here on Earth. So the breakdown of stratospheric ozone is a different process in terms of like obviously ozone into O2 and a single oxygen atom, and then a reformation of that's a natural process. That's formation and then the breakdown, right? But what we're talking about is like an artificial breakdown of the stratospheric ozone layer when chlorine is present from anthropogenic sources, CFCs, chlorofluorocarbons, that were used in propellants and refrigeration units, and are still in some refrigeration units. But we'll go over a little bit of the history of where this came from. But CFCs, there was a reason why they were produced, and it was a good reason, but we needed to find some technology that would work better. And so what happens is the CFCs will be like, let out of aerosol, or let out of a tank or something like that, and then they float up into the air, and the chlorine disassociates from the chlorofluorocarbon, and the chlorine is free floating, and then the chlorine is available to bond with an oxygen. So when the ozone is broken down, the chlorine binds to it, and now it's not available to be reattached to an O2. And so that oxidation right there interrupts the oxidation of O2 and the formation of ozone. So chlorine monoxide molecules, they react with a free oxygen, and then they pull that free oxygen out of the ozone producing process. A single chlorine atom can catalyze the breakdown, and here's where the danger of it is that chlorine is like, like UV was the catalyst for the breakdown of O3, whereas chlorine is actually the catalyst of a breakdown of O3. And it can break down as many as 100,000 ozone molecules until finally one chlorine atom finds another and the process will stop. So it'll be Cl2, it'll be bonded, but until then it's going to break down all of these ozones and pull them out of that process. In the process, ozone molecules are no longer available to absorb the UVB radiation. And so with the loss of ozone into just basically like being used in another process, now this chlorine is part of that concentration, we lose some of the filtering effects of ozone on Earth's surface, and that can lead to harm to biological organisms. So in the South Pole, like, Antarctica, it's actually really dangerous, and scientists that work there have to be really aware of that increase in UV exposure. Okay, there is a video, National Geographic video. It is attached in the assignment. But I really, I don't want to give it 3 minutes of my 15-minute limit, but it really does a good job of talking about some of the percentages of UV that are filtered. It really gives some visuals. So especially if you're a visual learner, I think it's really important for you to take a minute to stop and to watch that. It's only 3 minutes, and it's a really great, recap. But it also has some statistics that are notable that you should probably write down. Okay, so moving on, I just wanted to also give you a couple of resources here. This link, let's see if it'll take me to the link. All right, so this link works. This is an article from 2019 that talks about the size of the, actually in square miles, the size of the ozone hole and how it's the smallest since we discovered that it was actually, a problem. And we've been tracking this and watching it for a really long time. There are some reasons that are not necessarily because we've instituted a change in our use of aerosols, but there's still there's some good things that our humans are doing that we're rebuilding, and then some of it just happens to be chance. So it talks about how there's an ebb and a flow in the size of the ozone layer based on seasons, and then how this is the third time in the last 40 years that weather systems have caused warm temperatures to limit ozone depletions. And so the areas where ozone depletion happens the most are the areas that are really cold, and that cold air that's really high actually is associated with more loss in the ozone. This is just here as a resource for you to understand more about the mechanism behind how the hole formed and how the ozone layer behaves and what affects it. So let's head back into that presentation. This link is an informational link for you on just the basics of the ozone layer. This is through the EPA.gov website and how the ozone layer protects us, what is the history behind depletion. It takes us to the third link, and that is just a little history on the aerosol from the National Aerosol, Association. I don't really know what the National Association of Aerosol Producers, but that's just a little bit about the history of aerosols and how they're regulated, and there's a little Q and A. It is the association, so National Aerosol Association. It's okay to spray. That's what it says, but it's talking about what's being used instead. And I know you can't see all of this, but I really don't want to move my screen around because I got some things that there we go, that need to be up and running. So I did want to just bring you to this picture because it's amazing. This right here, and tell you a little bit about the history behind aerosols and why they were used in the first place. I didn't know this, and with a little digging today, I found this really interesting story. So refrigerators in the late 1800s and the early 1900s, which I was a refrigerator in the 1800s? I didn't even know. I thought they used ice houses. I don't know. So with the introduction of refrigeration, there was a use of toxic gases. So ammonia, methyl chloride, and sulfur dioxide were used as refrigerants. You've learned a little bit about some of those gases, and this is the issue though. Like, methyl chloride is highly poisonous. So after a series of fatal accidents in the 1920s where methyl chloride actually leaked out of refrigerators in someone's home, I guess, I don't know, the production was out looking for something that could replace these toxics, right? Frigidaire, General Motors, and DuPont. So CFCs were synthesized in 1928 by someone named Thomas Midgley, and he was a chemist at General Motors. And they were looking for large commercial applications, but then they started putting it, like into refrigerators, and then air conditioners, and then cars because of the air conditioning in cars. And then because of the, the safety record, like, it was way safer than poisonous gases in terms of it being non-toxic. Then it started to be put into a lot of different things, right? So as a propellant, this is where we think about it being used, is that after World War II, CFCs were used as a propellant in aerosols. These aerosol cans are really an interesting technological engineering device. They're really, really cool. They were relatively inexpensive. They made hairspray super convenient, and therefore CFC use and production took off. Well, then the hole in the ozone layer was discovered in 1974. Professors from 2 University of California schools, Professor Sherwood Rowland and Dr. Mario Molina, showed that CFCs could be a major source of inorganic chlorine in the stratosphere, and that their use would lead to the photolytic decomposition of ozone. And so this is a problem because ozone, being a trace gas, was known to absorb harmful UV radiation. They knew that that was there, but then they realized that the CFCs were destroying the ozone layer, and that was a problem. So no more CFCs. Let's see, I'm looking to see. I think in 1985, the US banned use, and then in 1987, nations signed a global environmental treaty, the Montreal Protocol, to reduce substances that deplete the ozone layer. So in 1987, signed into place the Montreal Protocol, and that right there, my friends, it's a notable, memorizable fact. Gotta get that one. Okay, let's head back into the presentation. Just 2 more slides. So this diagram here just shows the ozone concentration depletion levels from the 1970s on. So when we really began to start tracking what was happening. And you might ask, how do we track stratospheric ozone? We don't send people up. So I found this really cool picture to show the illustration of how it's tracked. Some of the meteorological wonders. And I just thought it was super pretty. And that was found on the NASA website. So it's a nice, well, I'll leave you with a really large form of that picture. This is a time-lapse photo, so it's not that many balloons. It's just the balloon floating really, really high up into, and it's called a ozone, I don't even know how to say that word. You can give it a try. But like a weather balloon. So it's a really, really light balloon, but it has instrumentation and sensors that will pick up on ozone concentrations, and that is one of the many scientific ways in which we track and measure some of these environmental issues.